All right, let's get straight into it. We're tackling a massive topic for your GCSE physics exam, the required practical on force and acceleration. Honestly, if you can get your head around this one, you're in a really good spot for the exam. So, let's do this.
So, here's how we're going to break it down. First, we'll nail the theory behind it all. Then, we'll walk through how to actually set up the experiment. After that, we'll look at the data and what it all means. And finally, we'll get you prepped for the kind of questions the examiners love to ask. It's basically a complete guide.
Okay, first things first. Before we even think about trolleys and pulleys, we've got to understand why we're even doing this practical. The whole point of this experiment is to get hands-on with one of the most important, fundamental laws in all of physics.
Now, this is the official wording, straight from the spec, and you've got to know it. But what does it actually mean in plain English? Well, it's pretty simple, really. It tells us two things. One, the harder you push something, the faster it accelerates. Makes sense, right? And two, the heavier something is, the harder it is to get it to speed up. That's it. That's the law we're about to prove. And this is the famous equation that wraps it all up so neatly. F equals ma. You've probably seen it a million times. F is our resultant force, and we measure that in newtons. M is the mass, always in kilograms, don't get caught out by grams, and A is for acceleration measured in meters per second squared. This simple little formula is the absolute core of what we're investigating today.
So let's talk about that M for a second. In this context, mass isn't just about how much stuff something is made of. We're talking about inertial mass, which is a bit of a fancy way of saying an object's resistance to having its velocity changed. You know, its stubbornness. A lorry has a huge inertial mass. You need a massive force to get it moving. A tennis ball, tiny inertial mass. It's easy to get that accelerating.
Right. We've got the why sorted. Now, let's get into the how. This part is all about the hands-on method, what you'll actually be doing in the lab to see this law in action.
And it's super important to realize this is really two experiments rolled into one. To properly test Newton's law, we have to look at two relationships: how changing the force affects acceleration, and then separately, how changing the mass affects acceleration.
And this slide, this is pure gold for your exam write-up. Knowing your variables is an easy way to pick up marks. So, in the first part, the force is what we change. That's our independent variable, and we measure the acceleration. But we have to keep the total mass of the system the same. For part two, we flip it. We change the mass and measure the acceleration, but this time the force has to stay constant. Get this right, and you're already flying. So, let's walk through the method for part one. You get your trolley, your pulley, your string, your masses. The weights on the hanger provide the pull, the force. You let it go, you measure its acceleration. Simple enough. But step 5, now this is the really clever bit. To increase the force for your next reading, you don't just add a new mass. You move a mass from the trolley and put it on the hanger. Now, why is that so smart? Because it increases the pulling force, sure, but the total mass of the whole system, the trolley plus all the weights, stays exactly the same. It's a brilliant little trick to keep your control variable perfectly constant. Here's the kit you'll be using. Now, let's be honest. The most important bit for getting good, accurate results is how you time it. You can use a ruler and a stopwatch, but light gates are the gold standard. They're connected to a computer, and they completely remove any errors from human reaction time. That means your measurements are way more precise. And trust me, that's exactly the kind of thing you want to mention in an exam answer.
Okay, you've done the experiment. You've got a page full of numbers. So what? This is the bit that matters. This is how we turn those results into actual grades. Let's get into the analysis.
For part one, you should end up with a results table that looks something like this. And you can see a clear pattern straight away, can't you? As we increase the force in nice, even steps, the acceleration goes up in a really predictable way too. This is looking good. It's exactly what we hoped we'd find.
Right, next job is to plot a graph. Now, you need to pay super close attention here. Normally, the thing you change, the independent variable, goes on the bottom x-axis. But for this practical, we're going to do something specific. We put the resultant force on the vertical y-axis and acceleration on the horizontal x-axis. This setup is absolutely crucial for the next step, and you're about to see why.
So if you've done everything carefully, when you plot your points, you should get a lovely straight line that goes right through the origin, right through 0, 0. This shape isn't just a coincidence. This is the graphical proof we were looking for. It's the perfect visual confirmation that force is directly proportional to acceleration. You double the force, you double the acceleration. Simple as that. And here's the big reveal. This is why we plotted the graph that specific way. Think about it. F equals ma.
If you rearrange that equation, you get mass equals force divided by acceleration. Now, how do you find the gradient of a graph? It's the change in the y-axis divided by the change in the x-axis. For our graph, that's force divided by acceleration. So, the gradient of your line is literally the mass of the system. How cool is that? It's just a really elegant way of proving the physics.
Now for the second part of the practical, where you were changing the mass. The analysis is very similar but with a little twist. This time, you're going to plot acceleration on the y-axis against 1 over the mass on the x-axis. I know, it seems a bit weird, but if you plot the reciprocal of the mass like this, you should again get a beautiful straight line right through the origin. And this confirms the other half of the law, that acceleration and mass are inversely proportional. And even better, the gradient of this line will be equal to the constant force you were using the whole time.
All right, we're on the home stretch. This is where we lock in those top-tier marks. An examiner doesn't just want to know you can follow a recipe, they want to see that you can think critically about the experiment itself. Let's talk about how to evaluate it.
Look, no experiment is perfect. And in this one, the main villain is almost always friction. You've got friction between the trolley's wheels and the bench, a little bit in the pulley, it's everywhere, and it's always acting against you, meaning your real resultant force is a tiny bit less than the weight on the hanger. Being able to talk about these errors is absolutely key for hitting those high-level analysis marks.
It's also vital that you know the difference between random and systematic errors. A random error is just that. It's random, unpredictable. Like maybe you start the stopwatch a bit late on one go. You can reduce these by taking lots of readings and finding the average. But a systematic error is different. It's a consistent problem that affects every single one of your results in the same way, like that pesky friction we just talked about. A big clue for a systematic error is if your graph's straight line doesn't go through the origin.
You know, what's so great about this practical is that it's a gold mine for exam marks because it covers all the bases. AO1, that's just knowing the method, and F equals MA. Easy. AO2, that's you applying your knowledge, doing the calculations, plotting the graph. But AO3, that's the top level. That's when you analyze the gradient, you discuss the sources of error, and you suggest smart improvements, like using an air track to get rid of friction.
So let's end with this. F equals ma isn't just some dusty old equation for a physics lab. Think about a car crash. Your mass is what it is. The change in velocity from 60 to 0 is huge. So how do you survive that enormous force? Well, seatbelts and airbags work by increasing the time it takes for your body to stop. By increasing the time, you decrease the deceleration. And if A is smaller, then the force, F, acting on your body is smaller, small enough to be survivable. The physics you've been investigating in the classroom, it's literally a lifesaver. Something to think about. Good luck with the revision.